My name is Arinda Josephine. I'm from St. Margaret, Katende. I'm going to be discussing Math Paper 2, number 15 and the numerical methods. So, number 15, part A, I've said that given that x is equal to 12.6955. So, they are telling us that truncate two significant figures. Truncating means we end at a specific position and then we ignore the rest. So when we are truncating this number to two significant figures, it's going to be 12. Then, when we go to Roman numeral 2, they're telling us to round off to two decimal places. So the two decimal places end here, but the number here is 5, and so it can be, we can shift the 1 from here and it goes here, but when it comes here to 9 it becomes 10. So we are first going to shift here and then it becomes 70. So the answer will be 12.70. Then part B, number 15, part B says, given that A is equal to 7.684 and B is equal to 0.31. So they are telling us that write down the maximum possible errors in A and B. To find the formula for maximum possible error, the formula for maximum possible error is 0.5 times 10 to the power negative n, where n is the number of decimal places. So our maximum possible error in A, our error in A is going to be 0.5 times 10 to the power negative 3, since A has 3 decimal places. So our error in A is going to be 0.0005. So we go to find the maximum possible error in B. It will be 0.5 times 10 to the power negative 2. Our maximum possible error in B is 0.005. So we are finished. Hence we are going to find the absolute error in the quotient A plus B out of AB. So I'm going to let this quotient to be Z. Let Z equals to this. So finding the absolute error, we're going to use this formula for absolute error. Absolute error is equal to maximum value minus minimum value, maximum value minus minimum value divided by 2. So we're going to first find the maximum value and the minimum value. So to find the maximum value, we are going to find the maximum value. We are going to find Z max, which will be equal to A plus B out of AB max. So this is the same as A plus B max out of AB min. So this will equal to A max plus B max out of A min plus A min times B min. So to find the A max, we are going to get the actual value of A plus the error in A, which will be 7.684, plus the error in A, which is 0.0005. Then B max, we shall get the actual value of B plus the error in B, which is 0.005, out of A min, which will be the actual value of A, subtract the error in A. Then multiply by B min, which will be the actual value of B, subtract the error in B, which will be 0.005. So our Z max is going to be, our Z max is going to be equal to 3.41353. This is going to be our value for Z max. Then we shall go on to find the value of Z mean. After finding the value of Z max, we are going to find the value of Z mean. So Z mean will be equal to A plus B out of AB mean. But this is also equal to A plus B mean out of AB max, which is also A mean plus B mean out of A max times B max. So to get A mean, we get the actual value of A, which is 7.684. We subtract the error in A, which is 0.0005. Then we add B mean, which we get the actual value of B, which is 0.31. Subtract the error in B, which is 0.005. Then out of A max, which is the actual value of A, which is 7.684, plus the error in A, which is 0.005, multiplied by the B max, which is the actual value of B, plus the error in B, which is 0.005. So our value for Z mean, is going to be 3.30019. After finding the value of Z mean, we are going to find the absolute error. Our absolute error will be the maximum value, which is 3.41353, minus the minimum value, which is 3.30019 out of 2. So our absolute error is going to be 0.05667. That was the first part B, Roman numeral 1. We go to part B, Roman numeral 2. Going to part B, Roman 2, which states that find the interval within which the quotient in B1 above lies. Our quotient was A plus B out of AB. They want us to find the interval within which this quotient lies. So we're going to first find the working value. Our working value would be this, which is the actual value of A, which is 7.684, plus actual value of B, which is 0.31, out of the actual value of A, which is 7.84, times the actual value of B, which is that. So our working value will be equal to 3.35595. This will be our working value. As the question states that we should find the interval, we are going to use this working value to find the interval. So, to find the lower limit, we are going to get the working value minus the error, the absolute error, 5595, minus the absolute error, which we got as 0.05667. So our lower limit is going to be 3.29928. Then we shall go on to find our upper limit. Our upper limit will be equal to the working value, which is 3.35595, plus the error, the absolute error, which is 0.05667. So our upper limit is going to be 3.41262. So since they told us to find the interval, we're going to write our interval like this. Here we shall start with the lower limit, which is 3.29928. Then the upper limit, which is 3.41262. So this is our answer. Thank you for listening.
My name is Florence from St. Mary Katende, and I'm here to discuss number 15 part C about errors. And it goes, the quantities P and Q were measured with errors E1 and E2 respectively. Show that the maximum relative error in P out of root Q is equal to absolute of E1 out of P plus a half absolute of E2 out of Q. Now, there are many ways of working out this number, but we are going to use this method of operationalization. We shall start by letting our function be equal to Z. P out of root Q. And delta Z be the error in Z. Now, this can as well be written as Z squared is equal to P squared out of Q. So from here, we are going to find our error in Z by adding Z plus delta Z squared is equal to P plus E1, which is the error in P squared, divided by Q plus E2. Now, when you expand this, you get Z squared plus 2Z delta Z plus delta Z squared is equal to P squared plus 2E1P plus E1 squared divided by Q plus E2. Now, from there, we shall rationalize this by writing Z squared plus 2Z delta Z plus delta Z squared is equal to P squared plus 2E1P plus E1 squared divided by Q plus E2 into Q minus E2. Also here up we write Q minus E2. From there we shall obtain Z squared plus 2Z delta Z plus delta Z squared is equal to P2 times Q is P2Q minus 2E1 PQ plus Q into E1 squared minus P squared E2 minus 2E1 E2P minus E2 into E1 squared out of, this is the difference of 2 squares, so we shall write it as Q squared minus E2 squared. Now, since delta Z, E1 and E2 are very small, since delta Z, E1 and E2 are very small, the quantities delta Z squared E1 squared and 2E1 E2P also E2 into E1 squared will approximate to 0, and we shall remain with Z squared plus 2Z delta Z is equal to P squared Q minus 2E1 PQ minus P squared P2 out of Q squared. Also, this one will approximate to 0 since it's very small. From there, we shall take Z the other side, and we shall remain with 2Z delta Z this side is equal to P square Q minus 2E1. This is E1. 2E1 PQ minus P square E2 out of Q squared minus our Z squared, which is P squared out of Q. Now when you simplify this, you get to 2Z delta Z as equal to 2PQ E1 minus E2 P square out of Q squared. From there we shall divide through by Z squared. By 2Z squared, and this side shall remain with delta Z out of Z as equal to 2Q PE1 minus E2 P squared out of Q times 1 out of 2, where our Z is Q, our Z squared is P squared out of Q. On rearranging this, we shall get our delta Z out of Z as 2Q1, 2QPE1 minus E2 P squared out of Q times Q out of 2 P squared. Now, when you simplify this, we shall obtain our delta Z out of Z as E1 out of P minus E2 out of 2Q.
Go.
Now from there we shall introduce the absolute verse, find the maximum relative error Z, and it will be Z out of Z absolute as equal to the absolute of E1 out of P minus E2 out of 2Q. Now from triangle quantities, this will be equal to E1, the absolute of E1 out of P plus E2 out of 2Q. From the tangent quantities. This can as well be written as delta Z out of Z is equal to the absolute of E1 out of P plus a half E2 out of Q. Hence, this is our maximum relative error in P out of root Q as required. The other part was saying, find the range within which 2.35 out of root 5.1 lies. Now, we are going to start by finding our working value, and to be given by 2.35 out of root 5.1. When you work out this, you obtain 1.0406 as our working value. Now, we are going to find the error in 2.35 out of root 5.1, and to be equal to the working value times the relative error. In 2.35 out of root 5.1. Now, when you compare 2.35 out of root 5.1 with P out of root Q, realize that P is equal to 2.35 and the Q is equal to 5.1 with errors in P and Q respectively. So the error in 2.35 will be equal to the error in the P, which is E1, and it is given by 0.5 times 10 to the power -2, where 2 is the number of decimal places in P, and to give us 0.005. Also, the error in 5.1 will be equal to the error in the Q, which is E2, and is given by 0.5 times 10 to the power -1, where 1 is the number of decimal places in 5.1, and this will give us 0.05. So, from there, we shall substitute into this formula for the relative error. And we shall replace the E1 with 0.005. Also, our 2 would be 2.35 plus a half the error in Q, which is 0.05, divided by the Q, which is 5.1. Now, when you work out this, you obtain 0.0070. From there, we shall find our maximum value. Our maximum value. From there, we shall find our error, which will be equal to the working value, which we obtained as 1.0406 times the relative error, which is 0.0070. Now, when we multiply that, we obtain 0.0073. From here, we shall find our maximum value. And our maximum value is given by the error in the 2.35 out of 5.1 plus the working value, which is 1.0406 plus the error, which is 0.0073. When you add that, you'll obtain 1.0. You obtain 1.0. Now, when you add this, you obtain 1.0479 as our maximum value. From there, we shall find our minimum value, and it will be given by the working value, which is 1.0406, minus the minimum, the error, which is 0.0073. When you subtract that, you obtain 1.0333. Now, from there, we shall find our range for 2.35 out of root 5.1. And our range will be written as 1.0333, which is the lower value, and then the maximum value, which is 1.0479. Hence, this was our number 15 part C. Thank you for listening.